In section 3.4, we're going to discuss zeros of polynomial functions. Recall that a rational number is any number that can be written as the ratio of two integers. So if you have a number that you can write in the form p over q, where p and q belong to the integers, then that represents what we call a rational number. A couple examples of rational numbers, for example, would be like the fraction 3/4, -2 over 7. Any whole number is also a rational number. For example, if I have the number 8, we can envision that as being 8 over 1. So if a number can be written as a fraction of two integers, then we would say that that number is a rational number. This is to contrast against numbers that are what we call irrational numbers. These would be things like your number pi, as well as things like the square root of 2. Those are not be able to be represented as a quotient of two integers, and that makes them irrational. There's a very important result that discusses the types of rational zeros a polynomial function can have, and this is what's referred to as the rational zero theorem. Let's suppose we have a polynomial presented in standard form. We have an x to the n plus an minus 1 x to the n minus 1. So it's written in terms of decreasing power of x. This is a nth degree polynomial, and it has integer coefficients. So we want all of these coefficients, the an minus 1, all the way down to the constant, we want to be integers. Okay. And let's suppose that p over q, so suppose we have some fraction in lowest forms, is a rational zero of f. If you have a rational zero of f, then it must be the case that the numerator of the zero is a factor of the constant term. In other words, the value p must divide a sub 0, and the denominator of the simplified fraction must divide the leading coefficient, a sub n. What this gives us is the potential possibilities for the rational zeros of a polynomial. If f has a rational zero, then it must be of the form p over q, where p is the factor of the constant term, and q is a factor of the leading term. So if we wanted to write out the possible rational zeros, all we need to do is form the factors of the constant term divided by the factors of the leading coefficient. So for example, if we look at, in this case, if we look at our polynomial in example 1, we have negative x to the fourth plus 3x squared plus 4. The leading coefficient, I'm just going to call that a sub n in this case, is negative 1. The constant term, and maybe I'll write it like this just so it'll be a little bit easier here in 2 seconds. So let's do this. So I'm going to put the a sub 0 up top. The constant term is the number 4. That's coming from right here. The leading coefficient is this value negative 1, which is right here. The next thing we're going to do is we're going to write out all of the different factors of these numbers. So we'll call this p, we'll call this q. The different factors that divide the constant term would be things like 1, 2, and the number 4 itself. And for the a sub n, the things that divide negative 1 are namely going to be 1. Now, technically speaking, we could have these all with either plus or minus signs, because plus or minus 1 both divides 4, as does plus or minus 2, and same thing with plus or minus 4. And then for the factors that divide negative 1, well, that's just going to be positive 1 and negative 1. So if we look for the possible rational zeros, we know that they have to be of the form p over q. So one possibility would be if we take the plus or minus 1 from p and put it over the plus or minus 1 from q. Or instead we could have the plus or minus 2 from p over the plus or minus 1 from q. Or we could have the plus or minus 4 from p and the plus or minus 1 from q. In general, we're not going to write this out like this all the time. You don't need to put the plus and minus signs with every one of these factors as long as you know it exists. Typically what I will do is I'll put the plus and minus out in front, and then I'll just list the factors of p and q like this. so that you only need to write one set of plus minus, because that covers all four possibilities. If we reduce these fractions ever so much, we get plus or minus 1, plus or minus 2, and plus or minus 4. So these would be our potential rational zeros of that polynomial. Okay. We're not saying that any of them, or specifically which ones are actually zeros of the polynomial, but we know for the fact that if this function, if this polynomial does have a rational zero, then it must be one of the numbers on this list. And if you think about like the subtlety and the implication of what this means, when we start off, if you're looking for rational zeros, right, a function in general, there's infinitely many rational numbers that are out there. So if you don't know the rational zeros theorem, then there's infinitely many possibilities for what we could potentially have as a rational zero for this function. However, according to the rational zeros theorem, any rational zero of the polynomial has to be of a certain form, p over q, where p and q are as described, and that cuts that infinite list down into just a handful of possibilities. What we'll do in the following problems is we'll actually go through and we'll check some of these to see whether or not any of them actually do end up being zeros, okay? So just be very careful here. We're not saying that they are zeros, but we're saying that these are the potential candidates to be a rational zero. Let's take a look at example 2. We're going to do the same thing. Let's write out the possible list for the rational zeros for the function f of x. So I'm going to start by writing out the constant term first. The constant term of this polynomial is -2. The leading coefficient is the number 15. Let's now find our list for p and q. And when I write out these values, I'm only going to write the positive values. What are the integers that divide 2? Well, we could have either 1 or 2. What are the integers that divide 15? Well, it could be either 1, 3, 5, or 15 itself. For the possible rational zeros, they have to be of the form p over q, where p is from the list here, and q is from the bottom list. I'm going to start by, let's say, picking the 1 from p and putting it over every type of possibility from the bottom of q here. So we could have, let's say, plus or minus 1 over 1, or we could have the 1 over the 3, plus or minus, it could be 1, and then we could use the 5 for q, or we could have plus or minus 1 over 15. Alternatively, if p is 2, we could have plus or minus 2 over 1, plus or minus, and that looks like a division symbol, sorry about that. My pen's acting a little wonky today. Plus or minus 3 over 1, plus or minus 5 over 1, and then lastly we could have plus or minus, what did I say, 5 over 1? Blah. This list just went off the rails real quick. Sorry, everybody. I'm still fixated on that ugly looking plus minus that looks like a division. So we could have the 2 over the 1, the plus or minus the 2 over the 3, or plus or minus 2 over 5, or lastly the plus or minus 2 over 15. And these would be all of our different possibilities. Of course, when you put something over 1, it's just going to be that number itself. So this would just be plus or minus 1. And similarly over here for this entry, plus or minus 2 over 1 would be just plus or minus 2. So this would be the complete list. These are all of the possible rational zeros for the function f of x. Let's now get into actually finding some of these rational zeros. Okay, so to find whether or not a particular candidate is actually a rational zero of the function, it's oftentimes easiest to kind of use that synthetic division. So if f of c, so if c is a 0, okay, then one of the things we recall for the remainder theorem is that would mean that f of x is divisible by the factor x minus c. We kind of saw that in the last section when we were doing the remainder theorem. So we can use synthetic division here to very quickly check to see whether or not we have a rational zero. Let's go through example 3. They ask us to find all of the rational zeros of f of x equals x cubed plus 2x squared minus 5x minus 6. So to start, let's look for the candidates. We do so by using the rational zeros theorem. We want to identify the constant term, which is negative 6. The leading coefficient here is going to be positive 1. Factors of negative 6 would be 1, 2, 3, and 6 itself. The factors of 1 would just be 1. And then our candidates have to be of the form P over Q. So starting with the list for P, everything's going to go over the candidate 1 for Q. So it's going to be plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, or plus or minus 6 over 1, which very easily simplifies to just plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So these are our candidates. And now what we're going to do is we're going to go through this list and start to see if we can find one. Generally, I start by working through the positive numbers first. And let's start with 1, because 1 is kind of an easy number to work with. So I want to check to see, is 1 a 0 of this function f? To do that, I'm going to use synthetic division, like this. I'm going to plug 1 into my blocks. The sequence of coefficients now goes directly across. It's 1, 2, negative 5, negative 6. And 1 will be a 0, according to the remainder theorem, if this remainder equals to 0. Let's find out. Remember, the first number comes straight down. To start the synthetic division process, bottom times block gives us 1. That goes under the next column entry. We add to go down, we get 3. Bottom times block gives us 3. Add to go down, we get negative 2. Bottom times block gives us negative 2. And add to go down, we get negative 8. So what does that tell us? Well, we got a non-zero remainder, which means that in terms of our candidates, positive 1 will not work. Okay, so positive 1 is not a 0 of this function. We still have negative 1 as a potential candidate, but at least for right now, we know that positive 1 is not going to be a rational 0. Okay. So let's try this again. And again, it might take a few tries until you find one that actually works. I'm just going to move up the list. Let me try the next positive value. Let me try 2. Is 2 a 0 of the function? Well, we bring the 1 down. Bottom times block gives us 2. Add to go down, we get 4. 2 times 4 would give us 8. Add to go down gives us positive 3. Multiply bottom times block gives us positive 6. And negative 6 and positive 6 add to go down gives us 0. So here, it does turn out that 2 is going to be a 0 for the function f. So we know that f of 2 from the remainder theorem from the last section, f of 2 is going to be equal to 0. Now, what else does that do for us? If 2 is a 0 of the function, then that means that x minus 2 is a factor of that polynomial. So we have right now a partial factorization for f of x. And I did not want to erase that, unfortunately. Let's bring some of this back. We had 2, negative 5, 1, and 2. My apologies. Let's bring this back real quick. 1, 2, 4. There we are. So we have this. So what we know right now is that we can write f of x. We know that x minus 2 is a factor because 2 is a 0. So we can write it as x minus 2. And this is our quotient. So remember from our polynomial division last time, the amount of times that x minus 2 divides into this would be given by this sequence of coefficients for our quotient polynomial. That's going to be x squared plus 4x plus 3. And the good news is once you get this part here, we can find the rest of the zeros by using our methods to solving this quadratic piece. This actually factors as x plus 3 times x plus 1. And so the other additional zeros from this thing, we know x equals to 2 is 1. To solve this one, you subtract 3 from both sides, we get x equals to negative 3. And this one will give us x equals to negative 1. So this polynomial of degree 3 has 3 zeros. All of them happen to be rational numbers. They are 2, negative 3, and negative 1. And notice that every single one of those values was on our candidate list, as they have to be, according to the rational zeros theorem. So in general, this whole idea of having to test to find a rational zero, it might seem like it's going to be a lot, but honestly, once you find a couple, once you whittle it down to what you have left is a quadratic, then we can use our methods for solving the quadratic piece to see where it's going to be equal to 0. Luckily here, this one factored, but we would even have things like the quadratic formula if needed. Let's take a look at the next one in example 4. We again want to find all rational zeros of f of x equals x cubed plus 7x squared plus 11x minus 3. So we need the constant term and we need the leading term. The constant term is negative 3. The leading term is 1. Factors of 3 are going to be 1 and 3. Factors of 1 are going to be 1. So our potential rational zeros, again, they have to be of the form p over q. They could be plus or minus 1 over 1 or plus or minus 3 over 1. So we get 4 possibilities here. They're going to be plus or minus 1 or plus or minus 3. Let's go ahead to see if we can find one. Let's start, again, I'll do synthetic division. Let's test positive 1 first. Let's see if positive 1 can be a zero of this thing. We have 1, 7, 11, and negative 3. 1 comes down. Multiply the bottom times block, we get 1. Add to go down, we get 8. Multiply bottom times block, we get 8. Add to go down, we get 19. Multiply, we get 19. Add to go down, we get positive 16. So we tested out positive 1, and we did not get a 0 here. It has a remainder of 16. So the positive 1 is not going to be a 0 of this function. So back to the drawing board, let's try a different value. I'm going to move on to the next positive number in the list. So let's try positive 3. See if maybe that works. The 1 comes straight down. 1 times 3 is 3. Add to go down, we get 10. Multiply bottom times block, we get 30. Add to go down, we get 41. Multiply, we get 123. And then add to go down, we get 120. Again, that's a non-zero remainder. So positive 3 is not going to be a 0 of this function. So 3 is out. Let's try some of our negative candidates. Let's try the first negative number we would have would be negative 1. So let's see if maybe negative 1 works. The 1 comes straight down. Bottom times block gives us negative 1. Add to go down 6. This would be negative 6. Add to go down, we get 5. Multiply, we get negative 5. And add to go down, we get negative 8. So it turns out that negative 1 doesn't work either. So scratch that off the list. There's just one more candidate left. So if this polynomial is going to have a rational 0, it's going to have to be negative 3. That's the only other possibility that we haven't checked yet. Let's go ahead and investigate that one. So is negative 3 a 0? 1 comes down. Bottom times block, we get 4. Multiply, get negative 12. Add to go down. Multiply, we get positive 3. Add to go down, we get 0. So it does turn out that x equal to negative 3 will be a rational 0. Okay. Remember, if x minus 3 is a 0, that means that x minus a negative 3, which is equal to x plus 3, is a factor of this polynomial. So we have a partial factorization. We have f of x So we have our partial factorization here, which is going to look like this. It's f of x equals, we have a factor of x plus 3, and then the remaining part of it is given by this sequence of coefficients, which would be x squared plus 4x minus 1. To find the remaining zeros, so for all of the other zeros of f, they're going to come wherever this factor is equal to 0. So to continue, we now need to solve where is x squared plus 4x minus 1 equal to 0 at. And because now we're down to the step where we have a quadratic, we can use our method for solving quadratic equations. Unfortunately, this one will not factor, so we're going to need to use the quadratic formula. A equals 1, B equals 4, and C equals to negative 1. So the other remaining solutions are going to be x equals negative 4 plus or minus the square root of 4 squared minus 4 times a times c, all divided by 2 times a. This is going to be equal to, doing some quick arithmetic here, this will be the square root of 20 over 2. X equals negative 4 plus or minus the square root of 20 breaks down. That breaks down into 2 radical 5 over 2. And this itself simplifies to negative 2 plus or minus the square root of 5. So this polynomial has 2 additional zeros. They are x equals negative 2 minus the square root of 5 and x equals negative 2 plus the square root of 5. So we've successfully found all of the zeros of f of x. Notice that of the zeros, only one of them ended up being a rational number, and that was the solution x equals 2 to negative 3. Okay. The other 2 zeros ended up being irrational numbers. But in general, we've succeeded because we've found all zeros for f. Let's take a look at example 5. We want to find all of the zeros of this polynomial, x to the 4th minus 6x squared minus 8x plus 24. Okay, let's begin by looking for the rational zeros. Let's write out our list of candidates. The constant coefficient is the number 24. The leading coefficient would be 1. The potential factors for 24 would be 1, 2, 3, 4, 6, 8, 12, and 24. And for Q, the only thing that divides 1 would be 1. Our list is going to be of the form P over Q. Here, everything's going to go over 1, so I can just kind of write it out more simply. It's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and plus or minus 24. So this particular polynomial has a lot of possibilities for rational zeros. The size of the numbers isn't what creates the possibilities, it's the number of factors that a number has. And clearly we can kind of see that 24 has quite a few bit of choices here. When I'm going through this list, I would always start off with the smallest positive value. So let's check to see if 1 is maybe a 0. So let's check 1. We're going to use synthetic division. And let's see what we get. The 1 comes straight down. This would be 1, add to go down, negative 5, multiply, add to go down, multiply negative 13, and we would get a positive 11. So what that tells us that right now is that positive 1 is not going to be a rational zero. Let's try the next positive number in our list. Let's try 2. Let's try the number 2. 1 comes down, bottom times block, add to go down, bottom times block. We get negative 8, add to go down, we get negative 16, and then multiply bottom times block, we get negative 32, add to go down, we get negative 8. So it turned out that 2 is not going to be a solution to this one either. Let's try another one. Let's try 3. So 1 comes down, 1 times 3 is 3. Add to go down, we get negative 3. Multiply, we get negative 9. Add to go down, we get negative 17. 3 times negative 17 is negative 54. Nope, excuse me, negative 51. And then add to go down. I'm not going to add it up, but clearly that's not going to be 0. So 3 doesn't work either. Let's try maybe 4. That's the next number in our list. 1 comes down. 1 times 4 is 4. Add to go down, we get negative 2. 4 times negative 2 is negative 8. Add to go down. 4 times negative 16 is negative 48. And 24 and negative 48 add up to give us negative 24. So this 4 doesn't work either. So we just keep checking our list.